Ladies and gentlemen, let's continue with internal forced convection, chapter 8. We are using the textbook of Cengel and Ghajar. And with the previous lecture, we've started with general thermal analysis of what typically happens with internal forced convection. And I started a page which I said you must please divide into two, where we do the constant heat flux on the left-hand side of the page and the constant surface temperature on the right-hand side of the page. So we've completed the left-hand part, which is the part of constant heat flux. Now we're doing the part of constant surface temperature. Why constant surface temperature and where do we get it? Well, many heat exchangers in industry actually have this situation. That is actually the most effective heat exchangers that you can get, and that is where there's a phase change. The phase change can be boiling, evaporation, or boiling, evaporation. I'm missing one of them, but in general, all the phase change cases that you can get actually falls into this category. Now, I'm not going to start in the beginning again. With the previous lecture, we've already indicated that the constant heat flux follows a linear line. That is now the fluid on the inside. But in the case of a constant surface temperature, that is not what happens. If you look at this temperature difference, you will see that the temperature difference is very high. So the driving force for heat transfer is very high at the inlet, but then it starts becoming less and less towards the outlet. And that's the reason why there's not a linear increase in the temperature. So it is incorrect to say that the average temperature difference for the calculation of the heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by the temperature of the surface minus the bulk, as we could do with a constant heat flux case. That is incorrect. It doesn't work. So what is the correct approach? Well, the correct approach is to look at a control volume inside the fluid of length dx, and then the convective stream, the m.cp Tm, the temperature of the fluid, the mean temperature, going into the control volume and then going out of the control volume, m.cp multiplied by Tm plus dTm, and then look at the heat transfer, which is not the total heat transfer, it is only for this control volume, is equal to the heat transfer coefficient multiplied by Ts minus Tm multiplied by dA, the area. And then we look at the heat transfer going in, which must be equal to the heat transfer going out. So the heat transfer in is equal to the heat transfer out. And I'm not going to write down the whole derivation for you. It is in the textbook. But what is important that you should take note of is that dTm is equal to minus dTs minus Tm. And because that is a constant, you can end up with an equation which looks like this. If you've made it simple and you've taken out all the left-hand terms, which is equal to the right-hand terms, is equal to the heat transfer coefficient Ts minus Tm, the perimeter P multiplied by dx. So that is just the heat transfer going in is equal to the heat transfer going out. Simplify it, and then you're going to end up with this equation. Now, here you can see that we're going to have a Lin solution. And the result is that you can write this as d Ts minus Tm divided by Ts minus Tm is equal to minus all the constants, the heat transfer coefficient multiplied by P, m dot Cp dx. So we've assumed that all this is constant, heat transfer coefficient also, and we look at it from the inlet temperature to the outlet temperature from x equals 0 to x equal L. This total length of this internal conduit or tube is equal to L, and the result of that is that we get an equation, the ln of Ts minus Te divided by Ts minus Te is equal to minus the transfer coefficient multiplied by the surface area m dot Cp. Okay. So, very important, the assumption is that the heat transfer coefficient is the average heat transfer coefficient. And the result is that, before we get to that, what I want to emphasize, and you'll see later on why I'm emphasizing it, is this part I would like to call the NTUs. It is in your textbook, but it is not so prominently used as I'm going to use in this module. So the number of transfer units is equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the Cp. So if we make this substitution, then we can say that the outlet temperature is equal to the surface temperature minus Ts minus Ti e to the minus h, the area divided by the mass flow rate Cp, or as I would, that is how it's in your textbook, but I would prefer to write it like this, e to the minus NTUs. Yep.
In this application, Ts and Tm will not be the same.
Correct. Ts is the temperature of the surface. Tm is the temperature of the fluid, which varies right through the channel.
The Cp, what would that be of?
Cp?
Cp changes.
It's a good question. What will happen with the Cp? The Cp will change, and you can go and check water. For example, if you have got an inlet temperature of 20 to 60, 4,180, and you can see it will change from 4,180 to maybe 4,160. So if you go and look carefully, you would see that the temperature change is very small. So normally, if we've got the outlet temperature, we take the bulk temperature still, and many of the experiments that is based on getting the heat transfer coefficient is actually based on the fact that we use the bulk temperature. And it's the same for the viscosity and the thermal conductivity K. For all of them, we usually do it at the bulk temperature. Okay. Oh, yeah, I see. Sorry. Here. Ts minus Te divided by Ts minus Ti. Any more questions? Okay. Okay. Now, what we now can do is we can take this equation, the m dot Cp, we can take it out and write the equation as a function of m dot Cp, and then we can go and put it into the equation of the heat transfer rate is equal to the mass flow rate Cp multiplied by the outlet temperature minus the inlet temperature. I'm not going to do all the mathematics, it's in your textbook, it's very elementary. And the result is that we are going to get a new temperature difference, which we are going to call the log mean temperature difference, the LMTD, the log mean temperature difference. And that temperature difference is equal to the temperature difference at the outlet minus the temperature difference at the inlet divided by the ln of delta TE divided by delta TI. It looks complicated, and in many cases it is written in your textbook that it looks more complicated than this, but it's actually a very easy equation to apply and to use, and I will show you later on. So there are two things that are now very important from this part of the work. Firstly, we have an equation that we can use to determine the outlet temperature. So when we've got the surface temperature, the inlet temperature, and the heat transfer coefficients, the mass flow, etc., we can calculate the outlet temperature. Now this outlet temperature is at the moment written for the total length L. But maybe we are interested in getting the temperature at a specific point. Now that's very easy. You can just make the heat exchanger length shorter. You can go and redo all the mathematics, and you are going to get the mean temperature at any point x is then equal to the surface temperature minus the surface temperature minus the inlet temperature, e to the minus hpx, hp is the perimeter, m dot cp. So here we can see the equation, and it's not in your textbook, is written as a function of x. So for any point you can go and calculate the temperature, which means you can actually go and calculate the temperature in the center of the tube. Okay. Now why do I want to emphasize this value of the NTU? We've got a tendency these days, because we can program everything, and on your laptop you can put in any complicated equation, and then when you do a design, you can just put in all the values and you get the answer. However, in many cases you lose perspective of what is actually driving the problem and what is so important and what is not important. And that is why this term is so important. It really tells us a lot of information. For example, I'm going to show you an example now. Suppose we've got a tube and the wall temperature is constant at 100 degrees Celsius. So everywhere that wall temperature is kept constant. The inlet temperature of the fluid, let's suppose it's water, is 20 degrees Celsius, and we would like to know the outlet temperature, and it has a certain area, doesn't matter what it is, and there's a certain heat transfer coefficient. If we now look at different values of NTU for calculating the outlet temperature, which is equal to Ts minus Ti e to the minus NTU, it's very simple to see that the surface temperature is 100, again 100, and the inlet temperature is 20. So we can now, for different values of NTU, go and determine the outlet temperature. Now, if we look at this heat exchanger, you've got a surface temperature there of 100. Here, the temperature at the inlet is 20. Okay. If you want to heat this water, then you've got many options. So you can maybe decide, I want to heat it to 100 degrees Celsius. If you heat it to 100 degrees Celsius, as the temperature rises, you just need to put in more and more heat transfer to keep on increasing the temperature. So you need a very big area if you actually want to increase it to 100. But maybe you would like to increase it to 50 or 40 or 30 or whatever, and this is how you can use the NTU method. So if the NTU is equal to 0.01, it's very easy. I can go and calculate the outlet temperature as 100 minus 80, e to the minus 0.01, and the outlet temperature would be 20.8. So it means that in this case, there's almost no heating. Temperature is 20.8. For the NTU of 0.01. Therefore, heat exchanger is not so effective. If we increase it to 0.5, the outlet temperature will increase to 51.5. 51.5 is about there. So that is for NTUs of 0.5. Okay, for 1, it will increase to 70.6. Okay, so that looks much better. Of 1. Now, if you increase it to 3, take note, the outlet temperature will be 99.2. 99.2 is almost going to be there. So the wall temperature is going to be 100. The fluid temperature is going to increase to 99.2. Only 0.8 degrees Celsius difference. If you don't have state-of-the-art thermocouples and a very good data logging measurement, you'll not be able to actually measure the temperature difference. So if you increase it to 5, the temperature will increase to 99.5, and if you increase it to 10, it will increase to 100. So for you as a designer, if you look at this, this is in many cases the place where you have to start doing a design. You can see that from 3 to 10, the NTUs has to increase by about 3 times. To increase the NTUs, you need to either increase the heat transfer coefficients or the area. Now let's suppose you've had a tube with a constant diameter and the flow was fully developed, then you would actually know what the heat transfer coefficient is, and the mass flow rate would be a constant, the CP will be a constant, so it is actually the area. You need to increase the area with 3 times to increase the temperature, outlet temperature, from 99.2 to 100. So, good rule of thumb for design work. Do not go higher than 3. Very effective already. 3 is an extreme case, but if you do a design and you end up with an NTU value of more than 3 and more, you must know it's already too high. You're doing something wrong, and you need to change your design. Right, now if you will remember, as I've said, you've done the work with a constant heat flux and the constant temperature, constant surface temperature. We've completed the left column, now we've completed the right column. So now I would like to summarize. Okay. And to summarize, we can say that, let's rather write it like this. The heat transfer coefficient is equal to the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the temperature of the surface minus temperature of the bulk for constant heat flux. Okay, CHF is constant heat flux. We also use that thing to indicate it is a constant. Constant heat flux, you can say it is equal to Ts minus the bulk. For the case of constant surface temperature, we have to use the LMTD. Okay? So the important thing in general is the LMTD. Now, if you've got turbulent flow, take note if it's turbulent, and you've got a constant heat flux. And if you then go and calculate the LMTD, you will see that delta TE is equal to delta TI. This is delta TI, that temperature difference at the inlet, and that is delta TI, the temperature difference at the outlet. Wait, no, okay, sorry. Okay, for constant heat flux, the delta T at the outlet is equal to delta T at the inlet. It's right here for turbulent flow. And especially if the tube is very long, it's a very good assumption. And then if we calculate the LMTD, is then equal to delta TE minus delta TI divided by the ln of delta T outlet divided by delta T inlet. What is going to happen? This term is going to be equal to 1. Okay, you see? If you've got a constant heat flux situation for turbulent flow and you use LMTD, then you're going to end up with LMTD of infinite. That value is actually going to be 0 divided by 0. So that's what you're going to end up with there, and then you see it doesn't work in any case. However, it's interesting to see that except for this case, you can actually use the LMTD for the constant heat flux situations also. Let's look at an example. We have a tube, and on the outside we have condensing steam. And the temperature is 120 degrees Celsius. Therefore, it's condensing, so there's a two-phase behavior, a phase change behavior. It changes from a gas to a liquid, the temperature of 120 on the outside, and therefore we can assume that the wall temperature would be constant 120. The inlet temperature is equal to 15. It's water, and the mass flow rate is equal to 0.3 kilograms per second. In this case, we are going to give the outlet temperature, which is going to be 115 degrees Celsius. And what is also given is the average heat transfer coefficient. The average heat transfer coefficient is equal to 800 watts per square meter degrees Celsius. And we have to determine the length of the tube that will give that to us, that boundary condition from inlet temperature of 15 to 115, and I think the tube diameter is 25 millimeters. Okay, how can the outlet temperature be higher than 115 and it is still water? the pressure is high enough. So if the pressure is high enough, this will not boil, so it will all be a single phase here on the inside. And therefore, again, we can now look at it and say the bulk temperature is equal to 15 plus 115 divided by 2, which is equal to 65 degrees Celsius. So at that temperature, we're going to get all the properties. So the properties for water, you can go and get it in table A9. And the properties for water that we're going to use is, it seems as if we're just going to use the CP value, 4187 joules per kilogram Kelvin. Now again, I want to show schematically this problem. Okay, that is the length L. We do not know how long it is. That is the temperature. Here we've got the tube. That is the inlet temperature. That is the outlet temperature. And we have the boundary condition that the temperature on the wall is a constant. If we thus now use different colors to show it with, that is the surface temperature of 115. And then we've got here the water temperature at 15 at the inlet, and the outlet temperature, 120. 120 degrees Celsius. Okay, this temperature is 115, so it's very close to the wall temperature. In terms of the outlet temperature, and we've learned that that is not what is happening. It is more something like that, and I'm going to illustrate that in more detail just now.
Sorry, sir, I'd just like to ask, why do you evaluate the CP value at the liquid state if there's this two-phase flow?
No, there's not. The two-phase flow is on the outside. So it's on the outside of the tube, or the inside, it's single-phase flow only. Okay. So what we are looking at the moment, you need to take some tiny steps to get to the case where you're also going to have boiling of the water on the inside. So you're first going to do forced convection, then mixed convection, and then when you do the course in the second semester, then we're going to do the boiling and the condensing part, how you're going to handle that. So we will get to that a little bit later, but it's in your textbook. Right. So there's the properties. And now let's see if we can go and determine the length of the heat exchanger. The heat transfer rate to the water is equal to the mass flow rate of the water multiplied by the CP of the water multiplied by the outlet temperature minus the inlet temperature. The mass flow of the water is equal to 0.3. The CP is equal to 4187. Outlet temperature is 115, inlet temperature is 15. So the heat transfer rate is easy, is 125.6 kilowatts. The heat transfer rate. We can also write it that the heat transfer rate to the water is equal to the heat transfer coefficient multiplied by the area, temperature of the surface minus the temperature of the bulk. We have the heat transfer rate, 125.6 kilowatts, is equal to the heat transfer coefficient has been given as 800. The surface area of the tube is pi multiplied by the diameter, which is 25 millimeters, therefore 0.025, multiplied by the length L, surface temperature 120 minus the bulk temperature 65, and we can get the length of the tube is 36 meters. Are you happy with that? I see many of you are smiling. Okay, this is exactly what I said you cannot do. Okay? So this is incorrect. Should be a lesson to you. Okay. Why? Because for a constant surface temperature, we cannot use this temperature difference as the driving force. We see that the temperature difference does something like that. So we need to integrate it to get the average delta T. And that is exactly what this equation is telling us. The LMTD should be calculated like that. Let's do it the correct way. Okay, so I'm going to show to you, this is going to have a 46% error. We should use the LMTD. Okay. Okay, now let me show you how easy this LMTD is. It can be very confusing when you have it in your textbook and you start to apply it. It is delta T at the outlet. Delta T at the outlet is that temperature minus that temperature. It's 120 minus 115. Okay? So that temperature difference minus this temperature difference, 120 minus 15. Divided by the ln of that term, the first term, 120 minus 115, divided by 120 minus 15. It's very simple. It is this temperature difference, 120 minus 115, minus 120 minus 15. There they are, and then the ln of that term and that term divided. Okay. So the LMTD works out as 32.87 degrees Celsius. Therefore, the heat transfer rate, correctly done, should be equal to the heat transfer coefficient multiplied by the area multiplied by the LMTD, the log mean temperature difference. The heat transfer rate is 125.6 kilowatts, equal to the heat transfer coefficient is 800 multiplied by the diameter multiplied by L, that is what we want to solve, and the LMTD is 32.87. Therefore, correctly calculated, this length should be 61 meters and not 36. So 46% error in your surface area required to get that temperature. Now, it's so worked out that in this case we do not have to calculate the NTUs. But let's just go and calculate it because it's a very good engineering thing to do, and it gives us a very good feeling for how good the design is. So the NTUs is equal to the heat transfer coefficient multiplied by the area divided by m dot Cp. The heat transfer coefficient is 800 pi multiplied by the diameter 25 multiplied by the length we've calculated just now. M dot is 0.3 and Cp is equal to 4187, and it gives us an NTU value of 3.1. So it is already on the upper limit of a good design. Actually, you can make it a little bit, you can decrease maybe the length to 3 or lower, but it's already a very high outlet temperature to reach when you get to 5 degrees. Normally, a good rule of thumb for heat exchangers is 10 degrees. 10 degrees difference is typically a good design. Okay. Any questions, ladies and gentlemen, on this very important part, paragraph 8.4, which is general thermal analysis, and I've spent now almost 3 lectures on it, so you must realize it is very important. Question?
So you still evaluate the properties at the bulk temperature, but not the LMTD?
No, you still calculate the properties at the bulk temperature, not the LMTD. What is the reason for that? The experiments has been done according to using that as the criteria. Okay. In terms of, now that we refer to that, in terms of the lecture of yesterday of Dr. Everts, there are 2 things that I wanted to add, but there were not enough time at the end of the lecture. The first thing is that you must remember that the equations that you see in the textbook is a selection of, to give you an idea what is going on. But every possible geometry is not taken up in the textbook, otherwise the textbook is going to be this thick. Just for natural convection, there's lots of information available and lots of equations and ranges. But every time you need to read the fine print to see if you are in range and if you can use the equation or not. For this course, you can use the closest one. Okay? It's not actually the right thing to do, but if in the test or exam you don't have other information, then that is what you need to do. So that's the first thing. The other thing was in terms of the geometries that were considered yesterday, maybe something like this, with different heatings and coolings, and the question was, well, what about the direction? Now the direction is, in many cases, a very difficult thing to determine or to know. There are some cases where it is very clear what the direction should be of the natural convection. Maybe in this case it is generally in that direction. But you have to remember that if the fluid is being heated on this surface, that it is going to collide with all the other molecules next to it. And the molecules, all the molecules are not standing still, they are all moving. Okay. So the collisions are not going to be totally in a perpendicular direction. There's always going to be skewed collisions, and that is what is actually going to force it. You must remember that we use the Mach number to determine if the flow is compressible or incompressible. Now, normally the velocities for natural convection is less than 1 meters per second. In many cases, much, much less than even than that. So therefore, the Mach number is so small that even with a gas like air, the fluid can be considered as incompressible. So therefore, you do not have a situation where maybe here at the wall, you get a molecule and then you've got another molecule here and they are scrumming against each other in terms of this one trying to get to that one. As I've said, they are all vibrating. Okay. They will only stop vibrating if the temperature is 0 Kelvin. But they vibrate and therefore the other molecule will come and most probably it will hit it like that and then it will force it in a certain direction. So there are many experiments where you can actually do an experiment, you can see what the direction is, and then tomorrow you repeat the experiment and then it's the other way around because of the instabilities that can occur, firstly. And in many cases, the geometries are not perfect. You know, this length and that length and that length cannot practically be exactly the same. And the geometry in many cases would therefore also have actually an influence on which direction the rotation will be of the natural convection. Okay. Paragraph 8.5, laminar flow in tubes. I keep, yep. Which section?
8.4.
8 point.
That is the question that you
Yes.
this example. If you don't have the exit temperature and you don't have H, would you then assume an exit temperature to get the fluid properties and
Yeah.
iterative process?
It's a good question. We're going to do it later on quite a lot. So in this case, you were spoiled by the fact that you were given the outlet temperature and the heat transfer coefficient. You're going to see that is in most cases exactly what you do not have. So therefore, if you don't have the outlet temperature, you can do one of two things. You can say, well, I'm going to take the average between 15 and 120 as my bulk and get the properties there. Or I know my heat exchanger is not so effective. You know, I hope to get to an outlet temperature of 50 or 60. Then you use 60 plus 115. You do the calculation, and then you get the new values, and then you just go and use that value to recalculate the bulk temperature. Normally, you don't have to iterate more than about two times, very quickly where it will converge. In many cases, you'll see that we can typically actually even use that value, and it will still work out fine. So that was the question in terms of the bulk temperature, in selecting the bulk temperature, and then you had another part of the question. Was anything else? Is that it? Okay. Okay. I actually now forgot to point out something very important. If we can just go back to that sketch before I forget. Okay. So if we now look at this, so this bulk temperature is 65. Okay. So this temperature difference, delta T average, would then be equal to 55 degrees. You see that? 55. Well, you would like to say that my LMTD that I've calculated, that temperature difference should be 32.87. So therefore, it should be that temperature, but it is not that temperature. Okay. That temperature you can calculate with this equation of the NTUs. You can go and calculate it with this. The LMTD is telling us that if we do the integration of that area, okay, then we're going to get a temperature difference, which is going to be that area there. Now, I didn't calculate that temperature, but you can go and calculate it. That would be the mean temperature, and then I'm going to draw it there. So that would be actually the LMTD. So that temperature that you can calculate at that point doesn't represent the temperature difference, as you can calculate with that. The real temperature difference of this problem, for that you need to integrate the area to get the average. Okay, is that clear? Right, laminar flow. There's still the last part that we do need to do of laminar flow in tubes. And we are not going to do the whole derivation, but there's a derivation in your textbook which is a very important one for the Nusselt number as a function of x. Remember, that is for fully developed flow, and that is for developing flow. And that distance, LT, is equal to 0.012 Reynolds Prandtl, the diameter. Okay, that is how you're going to determine that distance between developing and fully developed flow. Now, if the tube is circular, if it's a circular tube and we've got a constant heat flux, then the Nusselt number would be equal to 4.36, and you can calculate it analytically. Okay? You can calculate it analytically, and then you can also go and do it for a constant wall temperature. For a constant wall temperature, it would be equal to 3.66. So for both of them, it is for a circular tube. And again, I want to emphasize it's for a circular tube, so there are other geometries also. and they are given in table 8.1. And in that table, different geometries of tubes are given. Four or five of them. Again, it is just samples. There are many more available in literature. And depending on the aspect ratio, the values are given for a constant heat flux and for constant surface temperature. For laminar flow, all the Nusselt numbers are given there. But again, in the fine print of the textbook, in the fine print, it makes it clear that the Nusselt number is then equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by K. Because when you look at the Nusselt number of this one, the heat transfer coefficient multiplied by the characteristic length, what characteristic length should you use? The A value or the B value? The hydraulic diameter, which we've done previously, you use that to calculate the heat transfer coefficient from. So from this table, you're going to get the Nusselt number, and then you can solve the heat transfer coefficient as a function of the hydraulic diameter. That is not only true for the heat transfer coefficient, but also for the friction factor. So the friction factor, the pressure drop is equal to the friction factor multiplied by L, multiplied by the hydraulic diameter rho, the average velocity squared divided by 2. Now in this table, the friction factors are also given. So go and look at table 8.1, and you will see the Nusselt values and the friction factors of different geometries summarized in your textbook. Any questions, ladies and gentlemen? If not, thank you very much.